All right, welcome to Lecture 24, Part 1, Chapter 6, Section 3, the development of quantum theory, or quantum mechanics. So last time we walked our way through the Bohr model, a simple start to quantum theory, quantum mechanics. Now let's see if we can't, we are definitely going to follow how they figured out why it is the way it is. And it was thanks to a grad student named de Broglie. Yes, a foreigner, hence the funny pronunciation of his name, de Broglie. He said, look, we know that waves can act like particles. Okay, light is a wave, and yet it comes in individual packets of energy that we call photons. What if matter can behave like a wave? So what he proposed was that quantum mechanical objects have a wavelength, and when he worked his way through it, he found that the wavelength of a QM object would be equal to, or proportional to, I suppose you'd say, h over p, where this is momentum, which is mass times velocity. And that's why you don't have a wavelength, because you have a very large mass. No, I'm not calling you fat or anything. What I'm saying is that you're not an electron. An electron has a mass of 9.11 times 10 to the negative 31st kilograms. It has a wavelength. Okay, a wavelength approximately 10 to the negative 10th meters, all right, or 0.1 nanometers. It's on the same scale as the wavelength of light. You have a mass of approximately 70 to 80 kilograms. Okay, your wavelength is ridiculously small. Okay, you're essentially a classical object in terms of physics. Okay, you do not have anything in common with an electron, is what I'm trying to say. Okay. And they were able to confirm de Broglie's theory by firing electrons at a barrier with a couple of holes cut in it. Okay, it's the double slit experiment that they performed with ocean waves and light. Except instead of firing light at it or water waves, they fired electrons at it, and they saw the exact same interference pattern. Okay, they got bands with electrons striking. And in between, no electrons. Electrons are waves. Okay, this is known as the wave-particle duality. Okay, the dual nature of quantum mechanical particles is that they are somewhat wave-like and somewhat particle. In other words, you have a quantum mechanical particle. As it's flying through the air, it's not actually a particle in one spot. Instead, it is a wave-like smudge, okay, that exists somewhere across a region of space. Okay. So they are not in a single location. Instead, their location is spread out. And the faster they're moving, the more spread out they are. In other words, location and speed are linked. Okay? They're related to one another. They're not independent in the way we're used to thinking of them. And that's what leads to the Heisenberg uncertainty principle. You may have heard of this. This is the Heisenberg from history, not the Heisenberg from Breaking Bad. But the Heisenberg uncertainty principle states in mathematical terms the uncertainty in position multiplied by the uncertainty in momentum, that's mass times velocity, is greater than or equal to h bar over 2. This is just a small constant number And this is how precisely anyone or anything can know the position and momentum at the same time of a quantum mechanical particle. This is true for us, and it's also true for anything that wants to interact with the particle, including the particle itself. Okay. So it is impossible to know the location and speed of a quantum mechanical particle with perfect precision. There's always going to be some uncertainty there. Now, for a classical object, this number, this constant here, that's Planck's constant divided by 4 pi, that is so small that it doesn't really matter. But for tiny objects, it starts to play a pretty important role. Such that, for example, at 0 Kelvin, absolute zero, temperature is related to the kinetic energy of particles. So, how they're moving randomly. So they should, at 0 Kelvin, they should stop moving. But according to uncertainty, they can't. They're always going to be wiggling and vibrating and shaking around just a little bit. Now, another consequence is what's known as quantum tunneling. You fire an electron at a barrier. Even if the electron doesn't have enough energy to get through, there is some chance, no matter how small, that it will. Okay? That is tunneling. Okay? And that's the basis for, say, tunneling electron microscopes. Okay? It fires a beam of electrons at something and just measures how many make it through. It's also something you have to pay attention to in computer engineering. The people who build microchips, what they're building is essentially, a three-dimensional map, or a two-dimensional map for, electrons to move through. And they have to take into account the fact that the electron could sometimes tunnel from one spot on the microchip to another. So they have to be aware of that. Okay, so that's just one of the weird results you can get from quantum mechanics. So what does de Broglie have to do with Bohr's model? Well, think of a guitar string, or any string that is bound at both ends. You pluck it, and you get what's known as a standing wave, which has a wavelength. If the distance between the 2 points here is L, then the wavelength here is 1/2 L. It can't be, any less than that. Or, sorry, any more than that. Not 1/2 L, but 2 L. Yes. There we go. L equals 1/2 lambda. I knew I was getting something wrong. You can also get overtones. So here you have L equals lambda. And you can have 3/2. That's terrible. So L equals 3/2 lambda, and so on. Okay, so these are all standing waves. And it's because the string is bound at either end, you can only get specific wavelengths or specific frequencies coming off of that string. In the same way, you can think of an electron, with its wavelength, as being a bound standing wave around the nucleus. Okay, so here you have your nucleus, and your electron, with its wavelength, can only exist at certain distances where the circumference is equal to, some fraction multiplied by pi, because it's a circle, of the wavelength of the electron. Okay? If you got, at too small a distance, then the waves wouldn't overlap perfectly. Okay? You can only get certain specific orbits around the nucleus. That is what the de Broglie wavelength gives us, is it gives us a way to understand why electrons can only exist at particular orbits and not others. It's because it's a wave. And the only way it can exist at those orbits is if it positively interferes with itself. Okay, so its wavelengths have to overlap. It's like a standing wave on a guitar, only it's a three-dimensional circular spherical shell sort of thing. It's much more complicated than what I've drawn here, and you definitely don't need to know this mathematical formula up here. But that is how the de Broglie model, the de Broglie wave-particle duality, helps us understand the Bohr atom, why electrons can only exist at specific orbits around the nucleus. There are a couple of different mathematical ways of talking about quantum mechanical particles. One is with Schrodinger's wave equations. This is what people used at first. It was a really big, complicated, multi-dimensional, formula. Let's see, it was, let's see, R, theta, and phi. It was a complicated equation, and it was, huge, and it was big, and it was ugly, and it had imaginary numbers, and it had the letter E, and it was big, and but people were familiar with that math, so they worked with it for a while, as long as they had to. Nowadays, people use Heisenberg's, same Heisenberg as the uncertainty principle, Heisenberg's matrices, which it took them a while to realize that, a matrix full of, numbers, is, the same as Schrodinger's wave equations. But once they realized that, they switched over and now use these almost all the time because they're a lot easier to work with. You are not going to be working with either of them, though, because that's nasty, complicated math. Instead, you're just going to see the results. Okay, you're going to see the 4 quantum numbers. Okay. So first, we are going to start, well, what are they? The quantum numbers are sort of like an address for an electron. Every electron can be uniquely identified by the 4 quantum numbers. They tell you the location of the electron around the atom. So first up, we have N, the principal quantum number. N is a positive integer, meaning it can be, not 0. It can be 1 or 2 or 3 or so on. Okay. N is the shell or level or orbital. Okay. Tells you roughly, how far away the electron is from the atom. So the higher N is, the further out the electron is. So what you can think of it is as the floor on hotel atom. Okay. So the ground floor, the lobby, is the nucleus. And then, just N is 1, 2, 3, 4, how far up the electron is, how far out it is from the nucleus. Okay, next up we have L, the angular momentum, quantum number. Angular momentum is how fast you're moving in a circle. Don't worry too much about that. I'm giving you the names to try and hopefully make them a little bit more distinct. But L can be any integer, including 0, up to, but not equal to N. So 1, 2, N minus 1. Okay. So it is the subshell or sublevel. Oh, no. I'm sorry. N is not the orbital. Orbital is something entirely different. N can be sometimes orbit, but very rarely. Normally it's just shell or level. L is subshell or sublevel. Okay. You can think of it as the suite. Okay. So every floor on Hotel Atom has at least one suite of rooms, depending on how fancy it is. This is not the Hotel 6. This is, the Ritz-Carlton. You walk in, you have a lounge where you can receive guests, and then you have a bedroom, and you have a little kitchenette, that sort of thing. So L is what suite of rooms the electron has there on Hotel Atom. And next up, we have M sub L. M sub L is the magnetic quantum number. Now things are getting weird enough. Don't worry too much about what magnetic quantum number means. Just, it's another number, and it is also an integer, and it is from negative L to 0 to positive L. Okay. So if n was, let's see, say if n is equal to 1, L can be equal to 0, and M sub L can only be equal to 0. If n equals 2, L can be equal to 0, because that's less than n. M sub L in that case would only be equal to 0. Or L could be equal to 1, in which case M sub L is negative 1, 0, or 1. Now for n equals 3, L can be equal to 0 or 1 or 2, and M sub L is equal to 0 or 1, 0, 1, negative 1, 0, 1, excuse me, or negative 2, negative 1, 0, 1, 2. All right, so M sub L is the orbital. You can think of it as what room in the suite. Okay. So N is the floor of the hotel, L is what suite of rooms it's in, and M sub L is what room in the suite. Okay. It is also known as the orbital. So here, for n equals 1, that means the first floor has only a single suite of rooms, and that single suite of room only has one room. So it's the simplest, most basic suite. Okay. For n equals 2, you have two suites, 0 and 1. Suite 0 only has one room, but suite 1 has 1, 2, 3 rooms. And then on floor 3, you have 1, 2, 3 suites. Suite 0 has one room, suite 1 has 3 rooms, and then suite 2 has 1, 2, 3, 4, 5 rooms. Negative 2, negative 1, 0, 1, and 2. I know this is sounding confusing. Don't worry, we'll find a way to make it simple, but you have to know these numbers. The last quantum number, I said there were 4, here's the last one, M sub S. M sub S can only have 2 values, plus or minus 1/2. And this is the spin quantum number. Remember how accelerating a charged particle means that you get a magnetic field? Well, electrons act as if they were spinning. That's something you hear a lot in quantum mechanics. They act as if they were. It's just the way physicists have come up with for trying to understand these things in terms of old-fashioned classical objects. But plus 1/2 means it's spinning. It acts as if it were spinning, creating a magnetic field pointing up. Negative 1/2 means it's acting as if it were spinning, creating a magnetic field pointing down. So plus 1/2 and minus 1/2. So those are the 4 quantum numbers: level, sublevel, orbital, spin. N, L, M sub L, M sub S. Okay. And those identify every single electron around an atom. Okay, so this is the floor the atom's on, this is the suite, this is the room, and each room can hold only 2 electrons, top bunk, bottom bunk, because all electrons have bunk beds. plus 1/2, minus 1/2. Okay? And that is the Pauli exclusion principle. Named after Wolfgang Pauli. The Pauli exclusion principle says, one way to putting it is no two electrons can have the same four quantum numbers, or each orbital can only hold 2 electrons. So what does that mean for the atom? It means that for n equals 1, you have a single suite with a single orbital that can hold 2 electrons, 1 plus 1/2, 1 minus 1/2. On the second level, you can have L equals 0 or L equals 1. So M sub L equals 0, M sub L equals -1, 0, and 1. And this can have 2 electrons, 2 electrons, 2 electrons, 2 electrons. So as you go up to higher floors, you can fit more electrons onto each level. So the first one can only hold 2 electrons. This one can hold 8. Floor 3, the third level, can hold 18. The fourth floor can hold 32. In the next section, Chapter 6, Section 4, we'll be getting into all of this, and we will be making it easy. For now, I want to give you one last complication. Namely, orbitals have shapes. And what shape they have is based on the value of L. Okay. So for L equals 0, there's going to be, M sub L equals 0, and it is going to be a sphere. Okay. So, and those are called S orbitals. S for spherical. Okay. For L equals 1, you have those 3 orbitals, 1, 0, and -1, and those are shaped like peanuts. Okay. You have one like this, and one pointing in and out of the screen there. They're all shaped pretty much the same way. And those are known as p orbitals. P does not stand for peanut, but you can pretend it does. Pretend P is for peanut. Okay, PDB. All right. Next up, we have L equals 2. That's going to get us -2, -1, 0, 1, and 2. I am not going to try and draw all 5 of them, but they look like this. Sort of, but they're sort of arranged in 3 dimensions. There's 4 that look like this, and then there's 1 that looks like this. It's different. But there are 5 of them, and they are d orbitals. And finally, L equals 4, sorry, not 4, but L equals 3, our fourth and final, going from -3 +3, so there are 7 orbitals. These I'm not even going to attempt to draw because they are, hideous. It's a 3-dimensional. Okay, I'm just not able to draw it. They are a 3-dimensional sort of clover leaf. These are known as F orbitals. Now, what S, P, D, and F all stand for is actually something German. We're just sort of fortunate that S is sphere, P is peanut, D, let's see. D is for dumb luck, because 4-leaf clovers are lucky. Yeah, I have no hope of coming up with a really good mnemonic, but maybe you'll have better luck. F, the heck with that, because F stands for the heck with that. Yeah, I'm censoring myself a little bit there, but it's a three-dimensional sort of cloverleaf kind of thing. All right, so those are the shapes of the orbitals, the s, p, d, and f orbitals. Technically, the sublevels go higher than sublevel 3, than L equals 3, but we never actually see those in reality, okay? Because, well, we'll be getting to that in section 4. But for now, just remember, you have your 4 quantum numbers. Those are the floor, suite, room, and bunk, or level, sublevel, orbital, and spin. And those can be integers, other integers, less than n. This is negative L, integers up to positive L, and these are plus and minus 1/2. Okay. So those are the 4 principal quantum numbers. We will be getting into what those mean when we do Chapter 6, Section 4.